introduction. Welcome to this webinar, Introduction to the Simplest Magnetic Design Module, or MDM for short, part 1 with a focus on inductors. So I'd just like to underline at the beginning that this is a two-part webinar. In part 1, we will focus on inductors. Part 2 is next month, focusing on transformers. But in part 1, we will also cover some MDM basics which apply to both. So I would really like to emphasize that, to get the full picture, you should go watch both of them and in order. So if you're attending this and you want to get a colleague that's not here to watch part 2, to attend part 2, get them to afterwards watch the recording of part 1 first, please. So this is what we will be talking about today. We're going to start with a review of inductor modeling in SIMPLIS before we get into the magnetic design module material. Then we're going to talk about the level 2 model specifically, because this is what comes with the magnetic design module. Then we're going to have a basic introduction to how MDM is used and how it works. And then we will cover some design examples, a buck converter, a PFC, and finally, the design example you'll probably find the most interesting is the concurrent design example with a planar inductor. So we will save the best for last. So let's start with a review of inductor modeling in SIMPLIS. So this is, the most basic inductor we can have. It's a core with an air gap and a winding with some turns. So this core has a cross-sectional area, a magnetic path length, which includes also the length of the air gap, and as we said, a winding with a number of turns N. And when we apply a voltage to the winding or a current to the winding, this creates a magnetomotive force, or MMF, and it causes a flux to flow along the magnetic path inside the core. So how do we model this? How do we characterize this? If we're talking just about a magnetic material, which is what the core is made of, we talk in terms of a B versus H curve. B is the flux density in Tesla, and if we think back to our inductor from the previous slide, it's the flux, and here we use theta. You might be more accustomed to phi, but so it's the flux in Webers divided by the cross-sectional area in meters squared, and H is the magnetic field strength in amps per meter. And if we think to our back to our inductor, it's the number of turns times the current, which is the MMF, divided by the magnetic path length. So the slope of this BH curve in this case is the magnetic permeability mu, and this is how we characterize our magnetic material. Now, if we talk about a magnetic path, which is a core made of a specific material and including the air gap, we then talk about a flux versus MMF curve. So our flux is compared to the previous curve, B times A, the number of turns times the current through the turns. If we think back to the inductor, is our MMF, our magnetic potential. And if we think of an analog to an electric path, our flux is like current, and the MMF, which is the magnetic potential, is like our voltage. Then the curve, the slope of this flux versus MMF curve is the magnetic permeance, which if we think of the analog of the electrical path would be like the conductance, and therefore the inverse of this permeance, 1 over the permeance, is our reluctance, which is analogous to resistance in an electrical path. And then finally, we get to a magnetic device, an inductor. It's a magnetic material with a core structure, a path, and a number of turns. And then we are talking about a flux linkage versus current curve. Flux linkage is the number of turns N times the flux through our device. So this gives us Weber turns or volt seconds, which is equivalent. The current, of course, is in amps. And now the slope of our curve is our inductance in henries. And when we are specifying a magnetic device, such as an inductor in SIMPLIS, these are the specs that we want to enter. We want to enter a volt seconds versus current versus amps, so lambda flux linkage versus current I curve. And how do we do that? So we use the multi-level lossy piecewise linear inductor. In SIMPLIS, a nonlinear inductor is modeled using a piecewise linear flux linkage versus current, or lambda versus I characteristic, and there are 3 model levels. Level 0 models a piecewise linear inductor with a parallel shunt resistance. Level 1 models a piecewise linear inductor with a parallel shunt resistance and an equivalent series resistance, or ESR. And level 2, which is introduced in version 8.4 and because of MDM, models a piecewise linear inductor with a parallel shunt resistance and an ESR, but MDM is required for generating the level 2 model, whereas the level 0 and 1 models are entered directly by the user. So let's take a look. If I create a blank schematic, in the part selector, I go under magnetics, inductors, and I pick the multi-level lossy piecewise linear inductor, and I place it here. So when I double click, I get the dialog. Level 0, I can just enter a shunt resistance and a current versus flux linkage characteristic. On level 1, I get to add an ESR. And for level 2, I cannot enter anything automatically. I need to create the model with MDM. So let's go back to our slide deck. So again, level 0, as we said, piecewise linear inductor, shunt. Level 1, piecewise linear inductor, shunt, ESR. And now you might be thinking, well, flux linkage versus current is what I should enter, but I'm more accustomed to thinking in inductance versus current, L versus I, or that's what my data sheet has. So for entering the flux linkage versus current characteristic for the level 0 and 1 models, starting in version 8.4, we have an inductor conversion tool where you can enter the L versus I, and it will convert to a lambda versus I. And this is covered in the previous webinar, and you can check that out if that is of interest to you. So now let's talk about the level 2 model, because this is what we need when we are using MDM and what is generated when we use MDM. So the level 2 model is electrically identical to the level 1. So again, it's a piecewise linear inductance, a shunt resistance, and an ESR, but all 3 parameters are calculated by the magnetics design module. What's important to note is that the ESR in the level 2 model is the DC winding resistance only. And then without an MDM license, you will not even see this radio button to select the level 2 model. So if you're using 8.4 and later, and you only see level 0 and level 1, that's because you don't have an MDM license. So to create a level 2 model, I would click on this create with SIMPLIS MDM button, and we're going to get to that. But I want to draw your attention to this checkbox, which says write MDM generated model parameters to all lower model levels. If I uncheck that and create a level 2 model, what's going to be in the level 0 and 1 is whatever I entered previously. But if I check this, the level 2 model generated by MDM will be written into the level 1 model, so it will be the same because the 2 are electrically identical, and the level 0 model will be just the level 2 model without the ESR. And all these model levels will be consistent. And if you're wondering what would happen if I create a level 2 model with MDM and now pass the schematic, say, to a colleague who doesn't have an MDM license, well, he would be able to simulate that in the schematic, and he would get the exact same waveforms as you did, but he would not be able to create or modify the level 2 model because obviously he does not have an MDM license. So now let's get into the basics of MDM and how it's used. So MDM is not loaded up by default when you start SIMmetrix SIMPLIS. This is because loading up MDM adds some additional time. So it will be loaded the first time you want to create or modify a magnetic device using MDM or run a simulation with MDM. And MDM launches its own graphical user interface that consists of the following windows, and then let's go through them and see what they are. So if I go back to this lossy piecewise linear inductor, I want to create the level 2 model, and now I click on create with SIMPLIS MDM. So first there's going to be a splash screen, which unfortunately you're not seeing because I'm using 2 screens and it's showing on the other screen. But after some time now, here is the main MDM window. What happens in here? Here we are building a physical model of our inductor using a particular material, a particular core, and a particular winding. So there is a number of core shapes to choose from. From each core shape, I can select some predefined geometries. I can go and enter a customized geometry for each core shape, so I can modify here, each as you can see, each dimension of this core and create a custom geometry. So for example, change this. There are materials here, which are sorted by material type and by manufacturer. So there are several options. So to continue, let's pick, for example, a U-core. And this is a U-core where we can even specify multiple air gaps. So for example, I can say I want 5 air gaps, and it's going to draw that in this fashion. Once I have picked a core and a material, I go on to the winding tab where we define the winding. So we can pick a bobbin here. If there are predefined bobbins for this core, they will show up here. If they're not, you enter the dimensions. And as you change the bobbin height, you will see the visualization change. So now you see that our space for winding has reduced. And we can do that in back. And I can pick a wire size. So there are some predefined wire sizes, for example, AWG10, or again, I can define a customized wire. I can increase the diameter and say, well, this is 3.5 millimeters diameter. And I can pick different conductor materials, aluminum, copper drawn wire, pure copper, silver, annealed copper, and so on and so forth. And now I can enter number of turns. So for example, 10 turns, increase, decrease. I can play with how these turns are arranged. Because this is a U-core, I can split them across both legs. I can pick whether they're starting from the top or the bottom of the core, whether they are distributed or just one after the other, whether it's a hexagonal arrangement. So you can see here, this is the hexagonal and this is the square arrangement. And I can also add some spacing, whether relative or absolute, whether in millimeters between layers, or whether as a fill factor. So this will space out the turns more. And I can also make the windings multi-filer. So for example, I can make it bifilar in the X or the Y direction. And now you see this is a bifilar winding where there's 2 turns connected in parallel. Once I'm done defining this, I can go to the cooling tab and define the thermal properties of my inductor. The simplest option is no thermal modeling, where I just enter a temperature and I assume, okay, everything's going to be at say 55 degrees, and that's the temperature at which we will calculate our inductor losses. Or I can define natural convection, where I define an ambient temperature, the orientation of the core, and which sides of the core are open to convection. And I can say, there's no convection happening on the left side. And I can say on the right side, there's a heat sink with a certain thermal resistance. So you can model the presence of a heat sink or some other cooling system this way. Or you can also do forced convection, where in addition to everything for natural convection, you can define the direction of airflow and also the airflow speed. And this will be all used to calculate the temperature of the inductor when we run the MDM simulation. So, if I click cancel, nothing happens, and we haven't decided yet. We have to click finish. So I'm going to start off by showing a predefined example. So if I go to the welcome page, here I will find MDM Example Circuits. And for example, I open the simplest MDM buck converter, and this inductor has already been designed with MDM. So when I go to level 2, now it says I have a model, this is green. And once we click on editing it, the MDM main window comes up, and we see the design that has been built for this inductor. So it's an RM4 low profile core using N87 material, and here we have 2 turns of bifilar 19 gauge wire. So another window that's available here is if I click this button, this will be the output window. Now you will notice that while the main window is open, everything else is blocked. So you cannot interact with the rest of SIMPLIS. You have to close it. But for the rest of the windows, this is not the case. They can be, once they are open, they are on their own. They don't interfere with the rest of your operation. So in the output window, we see status messages like what is the initial inductance of our inductor, and what is some basics of our design. And here we will also see some output when we run the simulation. And if you're wondering where all these core shapes and winding shapes and dimensions and materials are defined, they are defined in something called MagDB, which you click this button to open, and which is a database which contains the definitions for all our materials, our cores, our wire materials, and our wires. So I can click finish here and make that go away, and now I can still interact with that MagDB and the output window. Here in the Core Materials tab, you can examine all the material data. So for example, for some materials, we have dynamic BH characteristics, which are BH loops. And for some, we have initial BH characteristics, which are BH curves, depending on what was available in the datasheet. And then you can also take a look at the loss curves and plot them. And you can see the loss curves, which we use to calculate the inductor losses. And you can pick, what you are plotting and change your axes and so on and so forth. I would like to point out that some materials have this plus sign next to them. That means that we are not using datasheet loss data, but our own measured loss data. And the difference is that our own measured loss data is measured with triangular flux and DC bias, which is what we usually get in power electronics circuits, or very often, whereas datasheet data will only have sinusoidal flux and 0 DC bias. So if you model your inductor with a material which has a plus next to its name, you will get more accurate core losses. So all of the data here is editable. You can add new materials, you can modify the existing definitions. For the cores, you cannot modify the shapes, those are fixed. Those new shapes are things we have to add as developers. But for each core shape, you can modify the existing geometries or add new ones. Same story goes for the conductor materials. Same goes for the conductor dimensions. So for example, for foils, we don't have any predefined geometries, but if you use foil windings and there's a foil winding that you use a lot, or certain sizes you use a lot, you can add them here. You don't have to enter them manually each time in the main window. They will just show up in the menu. Okay, so let's run an MDM simulation and see what happens. Before that, let's go back to our level 2 model. So another thing here is that it says here power probe calculates detailed losses using MDM post-processing. So in order to run an MDM simulation, and I will go back to the details here, you need to check this box, set the fundamental frequency of your inductor waveform, and also its wave shape. And once you have all that set up and have a power probe on the inductor, when you run, you will get, after the simplest simulation, this results window, which is showing us the detailed losses of this inductor. So we have core loss, we have winding loss broken down by type. We can see losses by winding or by turn. And here we can see also the effect of the proximity loss and of the fringing field of the air gap. So you can see that the turns which are closest to the air gap have a higher loss. We see the waveforms, not only the current and the voltage, but also the flux density in Tesla through the core. Here we see the L versus current characteristic. And here we have some details about the inductor design. And if we want to see the lambda versus I characteristic, we can right-click here on the inductor and say plot piecewise linear points, and now we see that lambda versus I characteristic. So how does MDM work? What happened here? We created a physical inductor model in MDM. From that, we got a nonlinear inductance characteristic and a DC resistance. We converted that to a level 2 lossy piecewise linear inductor model, lambda versus I, ESR, and shunt. We put that into our simplest schematic, which we simulated. We got our simulated inductor waveforms, and then we used those to perform MDM post-processing to get detailed loss results. And now let's take a look at this all with more detail, starting with the buck converter inductor design example. So here I have a buck converter. It's a 12 volt to 1.2 volt, 10 amp output, 500 kilohertz constant switching frequency DC-DC buck. This is the same buck converter that's developed in the simplest tutorial. Our desired inductance is 600 to 700 nanohenry, and we want to optimize for 50% load, so 5 amp DC. So here we don't have any MDM model, so we click on the inductor, level 2, and now I want to create a model. So let's pick, for example, an E30 core. To just pick a bobbin, which is available in the database, a 14-pin horizontal. And now let's open the output window to see, what we're designing. So what we want is 600 to 700 nanohenry, and right now we have about 500. So let's add more turns. And now with 3 turns, okay, that's way too much. So we want to increase the air gap. For example, 1.1. And now we have approximately our desired inductance. But we have still, so we'll pick an 87 core material and we'll get even closer. And now we have a core, we have an air gap, we have the correct number of turns, but we are still not using, the full winding area here. So let's add some more copper so we can reduce winding losses, and we can do that by making these windings bifilar. And we have an inductor design which fulfills our spec. Now when I click finish, that inductor model has been written to this here. In order to simulate it, I need to do 2 things with MDM. I need to add a power probe and place it on the inductor. and I need to check this box. So this is a buck converter. We have triangular current, so it's a piecewise linear wave shape, and we said that our fundamental frequency is 500 kilohertz. Now we're all set, and I can run the simulation. And now the post-processing has completed, and we have our results. So let's take a look at our inductor. We have 44 milliwatts of losses. Core loss is small at 5 milliwatts, but our winding loss is quite large at 39 milliwatts. Our DC bias current loss is 7 milliwatts, but our skin effect is 12, and our proximity effect is 19 watts. Since it's a large core, 13 cubic centimeters, it's not heating up very much from the ambient temperature of 25 degrees. But we can see here when we look at the losses by winding that this large air gap is causing some quite significant proximity losses in our winding. We can see here from the waveform that at 25 millitesla, our flux density is quite low in this material, in this core. And when we look at the L versus current, we can see that in this inductor is indeed oversized for what we need. So this, we're optimizing at 5 amps, and the peak current is 6.5 amps. The full output current of this converter we said is 10 amps. And here we see that this inductor starts to saturate, only around something like 75 amps. So it's really oversized for what we need. So we need to refine this design. But before we do that, I just want to compare what happens if I uncheck this power probe, calculates detailed losses using post-processing box, and just run the simulation that way. And now we have just a regular simplest power probe calculating the losses using the ESR, which remember is just DC resistance. And if we measure the mean of the loss in the inductor, what we're getting is 7.4 milliwatts approximately. And that's exactly what our MDM post-processing was telling us is our DC bias loss only. But you can see that the full losses are in fact 44 milliwatts. They're much larger because here we take into account the core loss and the AC winding loss. So let's improve this inductor design. So first we want a smaller core. So let's pick one of the smallest cores that we have at our disposal. This is an RM4 profile. And it's not showing any windings because here we have an error message. Winding is too large for bobbin width and height. That means that the wires we were using previously are too big. So let's pick some wires that can fit. So for example, 20 gauge. And this air gap is too large. So let's reduce it to something like 0.05. But still, our inductance is 1.8 micro. It's too high for what we want. So let's reduce the number of turns. And once we do that, we have 800 nano. So to get down to 600, 700, let's increase the air gap. And now we're at 611 nanohenry. Now, just to show what we can do, let's change this winding type from a solid round wire into a solid rectangular wire. So we don't need to have it bifilar anymore. And we can enter a dimension that is, going to nicely fill up our entire winding window. Right, okay. And now when I click finish, we will be writing this new model into our converter. And I have the previous results window open so we can compare, and let's run the simulation again. And right, of course, I forgot to click this box, so that's why nothing is coming up. Now, these losses are taking a bit longer to calculate because we're using square wire, but nonetheless, it's very fast. And now we can compare the two designs. So we see that even going to a smaller inductor, much smaller, so it's 0.84 cubic centimeters compared to 13 cubic centimeters, we've actually reduced the losses a bit from 44 milliwatts to 38 milliwatts. And because we have a smaller core and therefore a much higher flux density at 176 millitesla in the inductor, we have much higher winding losses, 25 milliwatts compared to 5 in the first design, because we've managed to drive down our winding loss. We have lower losses overall, but because the inductor is much smaller, it's getting hotter. So it's getting up to about 32 degrees versus 27, 28 in the first case. So, what is the difference? Our DC bias current losses are about the same. So if we were just using the ESR, we wouldn't see a difference in our simulation, but the post-processing shows us the difference. Well, because our proximity effect and our skin effect has gone way down, and that's because we have a much smaller air gap, and we are only seeing some proximity effect due to the air gap here at the edges of these square wires rather than all throughout. And if we look at the L versus current curve, we can see that now this inductor is saturating somewhere at around 11.3 amps. That's where it starts to go down. And this is a much better sized inductor for our application. So now you can imagine that you can keep playing with this, and you can pick maybe, what if I want, double the size? Can I get an inductor that's maybe 1.6 cubic centimeters, but it has even lower losses, and so on and so forth. And it's very easy to come up with an optimized inductor design using MDM in this way. So now, I will briefly go over a PFC inductor example. This is a 300 volt AC, 50 hertz input, constant on-time PFC rectifier with 400 volt output. Our desired inductance is 430 micro, and the peak inductor current is 2.6 amps. I am not going to go through the design. It's actually one of our example circuits, and I'm just going to run it. So first, our circuit simulation is taking a bit longer because it's a PFC. So, coming off the 50 hertz input. Here we can see the inductor current. And now the losses are taking a bit longer to calculate because we have to go through the entire PFC waveform. And here are the results. So because I haven't opened the main window to show you the inductor design, I can go through it through this Inductor Design tab. It's an ELP58 core, 3 air gaps with 3 E27 material, 0.5 millimeter air gap on all 3 legs, and we're using 405 strands of 41 gauge wire to have a Litz wire with 30 turns. And this is how our inductor is built with a hexagonal arrangement of the turns. And you can see again how there's more proximity loss here close to the air gap. And again, here also close to the air gap. We can see here that we have 124 milliwatts of core loss, 72 milliwatts of winding loss. Our total losses are 196 milliwatts. And because again, it's a fairly large inductor, we are getting only a 2 temperature rise compared to ambient. So what is important to note in the PFC example is, one, when we look at the waveforms, we have an entire, or in this case, half a line cycle. And when we are calculating the core losses, every single one of these piecewise linear segments of the flux is being parsed, and the core losses are calculated for it. And that's why it will take significantly longer to do than with just a buck, where it's just one triangle rather than, you know, tens or hundreds of them. And to run this example properly, when we set up the post-processing parameters, we have to properly select the wave shape. In this case, it's a rectified sinusoidal with piecewise linear ripple. So you can see this is a rectified sinusoidal. It has piecewise linear ripple, and that's what we need to select. And then there's the fundamental frequency. Now, I did say this is a 50 Hertz input line, but since it's rectified, both halves are the same. So to make the simulation go faster, it's enough to enter a fundamental frequency of 100 and just process 1/2 of the line frequency. If this was not a rectified sinusoidal, but just a sinusoidal with piecewise linear ripple, then you would need to enter 50 Hertz here. Okay. So now let's go to the final example and the most interesting one, which is the concurrent design example using a planar inductor. And I want to first explain what I mean by concurrent design. So when we have an inductor, which is a magnetic circuit, you know, what is it affecting in the circuit? Well, it's affecting obviously our inductor current ripple, which is affecting our inductor loss, and that's what we saw when we were, you know, running the post-processing in the previous examples. But it's also affecting, you know, that inductor current ripple is also affecting our peak and RMS current through the switch and the diode, and that's obviously affecting our switching and conduction loss. And it will also affect our capacitor ripple and loss. And of course, L and ESR will affect our control loop dynamics. So we can see that magnetic and electric circuits in a power supply are tightly coupled. They're affecting each other back and forth, and it would be ideal if we could design them concurrently. And this is what MDM enables us to do. So using the same buck converter as before, we want to design a planar core with planar PCP windings, planar inductor, and decide whether we want to use a 2-layer or a 4-layer board. So I've already prepared these in advance. So assume here that, for example, you are the electrical designer, I'm the magnetics designer. You've come up with your circuit and you say, you know, we have this, you know, I want to do a planar design because that's, you know, fitting in my space requirements. And I know we have this planar core that we can use here, but I don't know how to design the inductor itself. So you're asking me, the magnetics designer, hey, how do you design this inductor? I could use a 2-layer board or a 4-layer board. What do you need me to do here? So, you know, if you made the assumption that everything's fine with a 2-layer board and, you know, you made your design that way and you send that off to the magnetics designer and he comes back and he says, look, I can't do that, then, you know, you've got a problem. You have to start again, or you have to change your inductor specs or something like that. Here, we can say, well, okay, let's look at what we got. So this is a customized planar core using N87 material, and using the solid rectangular windings I previously showed you to just do rectangular wire, we can actually model a PCB trace. And this is 2-ounce copper, which is about a 0.07 millimeter thickness of the PCB trace. And the space in between here is about 1.4 millimeters, which is the FR4 standard thickness for a, or sorry, 1.6 millimeters, which is the standard FR4 thickness for a 2-layer board. And voila, we have modeled our planar inductor. And we can run the simulation. And we get some results, and we say, you know, with the 2-layer board, we have 254 milliwatts of losses. Core losses are quite small part of the total at 24. Winding losses are the biggest. Really, it's DC bias, that's DC losses that are the biggest because this is a very thin trace, but we can see that there are some proximity losses here due to the air gap, and also some AC conduction losses. And then we can say, well, we can immediately try the 4-layer board, which is using 1 ounce copper. So here, it's the same core, but now the 1 ounce copper thickness is 0.035 millimeters. And because we only need 2 turns to get the desired inductance, we make it bifilar to use all 4 layers. And of course, this is a different interlayer spacing because, you know, you can get different spacings. The 4-layer board can be thinner. And now that we've modeled our 4-layer board, we can again run the simulation. And do a comparison. So now we can see that in this case, there isn't really that much of a difference. So the total losses with the 4-layer board go down a bit to 224 milliwatts. So it's a 30 milliwatt difference. Core losses are the same as expected because we have the same core and the same flux density, but our winding losses have gone down by about 30 milliwatts. We've managed to somewhat reduce our DC bias loss, but due to the different arrangement of the turns in the window and compared to the air gap, our proximity losses have almost gone away. But because we are using a thinner trace, now we have more skin effect loss. So that is the comparison of the 2 inductor designs, but this is giving us a lot more information in this kind of concurrent design methodology, because if I'm picking a 2 or a 4-layer board as an electrical designer, this is affecting so much in my circuit. You know, how am I connecting in the other components? How are they going to behave? The cost of this board, and to be able to know quickly, talking to the magnetics designer, you know, what's the design going to be with a 4-layer board or a 2-layer board, whether it's possible in the first place, and to compare them. That makes it much easier for me to make my other design decisions. And you know, we can go back and forth really quickly and say, well, if I tweak this in my electrical circuit, what's going to happen with the magnetic device? Or if you tweak the magnetic device, what's going to happen back and forth? And then kind of at the same time, we can optimize both our electrical circuit and our magnetic devices. So to kind of recap what we've done here, a similar range of topics is covered in this webinar, is covered in chapters 1 to 3 of the Simplest MDM tutorial. So if you have not gone through the tutorial and you want to go over the material here in the webinar, I would suggest going through those chapters. It's not identical, but it's similar. We've gone through some basics of how to use MDM and how it works. We've done some design examples, and we've looked at concurrent design and the fact that MDM enables the concurrent design of the electrical and the magnetic circuit and a high bandwidth communication between the electrical and magnetic designer. So it's not just a tool which allows you to design and simulate an inductor or a transformer. It's a tool which creates a platform for close and efficient collaboration between people doing the electrical design and the magnetic design, or if that's the same person, gives one platform where that same person can do both. And we will be covering transformers in part 2, and that will be our next webinar. So thank you for listening, and now we have time for questions.
All right, thank you, Andrea. There are a few questions in that we're going to handle right now. Feel free to If you think of any questions, go ahead and submit them. But first question is, can MDM build a bifilar coupled inductor where each winding is a separate inductor? And if not, when or if will MDM be able to model such inductors?
To get that on the schematic, as in, these are two separate coupled inductors on the same core. That's not something that we can do yet. It is something that we are working on, but I can't give you any timeline as to when it will be available. I think it might be possible to model this using the transformer, but I would have to think about that and see what kind of arrangement in particular you're trying to model. So maybe you can send me an email on that topic, and I'll think about it in more detail.
All right, next question we have is, for planar windings, do you calculate the capacitance between layers?
No.
All right. And last question I see, keep in mind, or please, if you have any questions, go ahead and pop them into the questions panel. Does MDM include, I think that's supposed to be toroidal core shapes?
Yes, yes. So if you open the inductor, so we can pick a toroid shape. So as you can see, here is a toroidal inductor. So yes, toroidal inductors are a bit more limited. Like, we cannot do the bifilar wire, and we can't do foils, and we can't do square wires, so round wires only, whether solid or lit. But yes, we can do toroidal inductors.
Alrighty. And how difficult would it be to automate the planar inner winding capacitance?
Well, this is, this is a not simple topic, and so far we have not been able to find any simple models that are general enough that we would have confidence, showing you as a result. I understand that the planar one, like the example I showed, would be quite easy to calculate, but if we would add this, we would have to have something general that, regardless of how you arrange your windings, you would get a number, and this is not something we have in the moment. So, it's not something that's coming soon.
All right, next question is, does MDM have a library of standard multi-strand wires to minimize skin effect losses?
Yes. So if we open the database here, and we go to the conductor dimensions, and we go under Let's Round, so here are some standard Litz wires, and it's, for example, 38 gauge wire with 10 strands, 38 gauge wire with 12 strands, 135 strands, then 41 gauge wire with 60 strands or 90 strands, and of course you can add your own. So if you don't see, there's 41 gauge 90 strands, but you use 95, for example, you can edit this and say, this is 95, and say save as, and now we've added, there was 90, now we've added 95. So you can grow this library based on what you have available.
All right, I think we got one more question. Can Z windings be modeled?
Z windings. I'm not sure what the question means by Z windings. Maybe if you would send me a picture of what you mean by email, then I will be able to answer that question.
I think the Z windings, it might be referring to a zigzag transformer, but that's a transformer, so we'll be
Yeah.
we'll follow up with that question separately to the asker. Give a minute or two if you have any more questions. Alrighty, looks like we're all finished up. So